Krongi, can you turn off your rock and roll music, please? I'm trying to make a video.
Oh my god, you're Krongroot.
Thank you. Thank you very much. You can put on your headphones. Sorry, okay, it was actually my music. Class, welcome to another lesson of late night physics. I'm just going to go through a few things tonight. One of them is kind of difficult, the other one's pretty simple. And just like the last one, these are things that are going to be on the quiz that we're taking this coming Thursday. In case you're still not for sure about the schedule next week, let me just reiterate that. Monday is bridge testing. Tuesday is the presentations. Wednesday, some of you I will see in class and some of you I will not, because we'll be doing the ACT and PSAT testing. So I'm just going to write ACT/PSAT, just depends on what you're doing. We'll have a kind of a different schedule that day, so for example, I don't even think I'll see first hour at all, but then I will actually see, what is my other hour? Fourth hour. Yeah, I think I'll actually see you guys. So some of you I'll see on Wednesday, some I won't. Thursday will be the quiz. Oh boy. Maybe presentations if we don't get through them all on Tuesday. We'll just kind of have to see how that goes. And then Friday, probably we'll do some new material. Okay. For today, we want to review what net force means. So I'm going to talk a little bit about the net force on an object and what it really means, whether or not there's acceleration. And the other thing, it's just two things today, is forces at angles. That will be a rather challenging thing, and so I hope to do at least two examples completely involving forces at angles. Okay. So, net force, I just want to reiterate this because there's a couple questions not only on the quiz but that you'll encounter quite often where, let's say that an object has a constant velocity, like for example a car. There, that's a car with a, okay, that's not a very good car. Okay, this is a car, but that's a window. It's a Formula One race car. Anyway, point being, you've got a car going this way with a constant velocity. Now, is this object accelerating? No. Constant velocity automatically means no acceleration. Now, if I draw a force diagram for this object, there would be a force due to gravity going down. There would be a normal force. I'm going to put F of n going up. And let's suppose that we actually have, usually you would not draw this unless you were told to draw this. Only if you're told to draw this would you actually draw this. I'm going to call it wind resistance. So wind resistance would be going against the motion. So I'm going to put this way. I'm just going to put force of R, F of R for wind resistance. In order to counter the wind resistance and keep the velocity constant, then there must also be an applied force coming from the tires of the car. So we've got four different forces acting on this object, one perpendicular to its surface, one as a result of gravity, one is the resistive force of the wind, and the other is the force of the tires pushing the car in the forward direction. These are all the forces acting on the car. And I must have a force in each direction, or at least any direction where there is one force, then there must therefore be another force going the opposite direction because it's constant velocity. Well, the question you might encounter sometimes would be, what is the net force? A net force, in a way, means you take all the forces in each direction and add them up. So, the force in the x direction, I've got let's say that over here is negative and over here is positive. We'll say down is negative and up is positive as well. Well, in the x direction, that's the horizontal force, or I'm sorry, I'm not drawing this very well. There we go. Sum of the forces in the x direction. This is the sum signal, and here's my signal, or variable force in the x direction. I'm going to list all my forces. Negative F of r, positive force applied. There's no acceleration, so it's 0. Sum of the forces in the y direction. Negative mg, which I could have called this one force due to gravity. Either way, whatever you want to call this, if you want to write mg or you want to write f of g, that'd be totally fine. Right here I'm going to write mg, and it's negative, and the normal force, which is positive. Now there's no acceleration going up or down either, so I also put 0. What is the net force? In any direction, 0. There is no net force because all the forces cancel each other out. Or basically they are equal to the opposite sign, like a positive in one direction is equal to the negative force going the other direction. And so, when all the forces are added together, in order for there to be no acceleration and constant velocity, the net forces must be 0. There might be at least 2 questions on the test that will ask you something along those lines, possibly. So keep this in mind. If there's no acceleration, there's no net force. And that's not important just because you're going to take a quiz with that question. That's important because you need to use this again in other problems later on. Okay, so I did the first part in only 6.5 minutes. Hopefully the second part I can finish in about 9 to 9.5 minutes, and we'll have this video wrapped up in about 15 minutes. That'd be pretty awesome. All right, forces at angles. All right, for this one, I'm going to do a single force applied to an object. Let's say, I'm sure everybody around, that's a terrible drawing. Oh my goodness, terrible, terrible, terrible. Let's say that we have a surface of not smooth, but a rough surface, and you're pulling there we go. Alright, so what we have is a person pulling a box with a certain amount of mass M, and they're pulling it in this direction, and they're pulling it on a rope that makes a little bit of an angle. And if I measure the angle of the rope that they're pulling it with, this angle makes I'll just call it theta for now, makes an angle theta with a horizontal. And I drew this dotted line simply as a horizontal reference, obviously, parallel to the floor, but this is the angle of the rope. So in a way, they're kind of pulling it up and pulling it to the right at the same time. So what this does is it basically, in a way, lightens the force due to gravity, or I should say, lightens the weight of the object, but also pulls it in the right direction. And what we want to know is, let's say we want to know what is the total force being applied. Find net force. And the net force could be in the x direction and also the y direction. I'm going to do both of them. So, first I should draw my force diagram. I'm going to put F of G this time going down. I've got a normal force, F of N, and then right here we have an applied force, F of A. And since this is a rough surface, we also have a resistive force going this way, F of F. Well, first of all, oh my goodness, it's the police. It's pretty funny. First of all, let's say I just want to find the components Let's say I just want to find first the components of the applied force. I need to do this before I can get the net forces. So to get the components, I've got to take this vector right here that's at an angle, and I have to find the force in the horizontal direction and the force in a y direction. Well, if I take just this little piece right here and draw it again over here, I'm going to make a triangle. Oh boy, a triangle sounds kind of like trig. Here's the horizontal direction. There's applied force. Of course, I have a right angle in there in reference to the horizontal direction. Here's my F of A. I'm going to call the applied force, or make the applied force, I'm going to make it the hypotenuse. And here's my force in the x direction, and here's my force in the y direction. X direction is being pulled this way, y direction is being pulled this way. And as you can see, if I was given the force in the x direction or the y direction, well, I would draw the x direction first, then draw the vertical or y direction, and it would make a triangle, and I could use a Pythagorean theorem to get f of a. Well, I can't use a Pythagorean theorem if f of a is the only one I have. I'm also going to put my angle right there as well. However, if I've got the angle and the hypotenuse, I can go backwards and get f of x and f of y. I'm going to write up here something that you've seen many times, SOHCAHTOA. Oh boy. Sine is the opposite over hypotenuse, cosine is the adjacent over hypotenuse, and tangent is the opposite over adjacent. So let's go ahead and do the sine one first. Sine, of the angle theta equals the opposite, f of y, divided by the hypotenuse, f of a. Well, I want to solve for the component, which is the f of y. Boy, this sure is difficult. F of y, therefore, is equal to multiply f of a by both sides, and I get f of a sine theta. So, if I want to find just the vertical force, then I just simply take the applied force multiplied by the sine of the angle that it's making with a horizontal, and that gives me the component in the vertical direction. Let's do the same thing with a cosine. Cosine of theta is equal to the hypotenuse, is equal to the adjacent, which is f of x, divided by the hypotenuse, which is f of a. When I solve for f of x, I multiply both sides by f of a, and I get f of a multiplied by the cosine of the angle theta. Now I can do my net forces. Leave that there for a moment so you guys can write that down. Now, this is... Sorry, I should have written that underneath of there. There, that's how I get the components. Now I'm going to go back and do the net forces. Okay, let's do the vertical ones first. So the sum of the forces, this may, in the y direction. I realize now that you're probably going to dislike that I'm going to write sum of forces in the y direction like this, and then here we have a component f of y. This and this is not the same. I'm saying the sum of forces in the y direction. Just remember, this right here is one thing, and it's not the same as this. Okay, I'm sorry if that's kind of difficult to remember. You just have to remember that it just is. Or if you want, I can just put like a little colon right here. Okay. Sum of the forces in the y direction. Once again, I'm sorry, I need my positives and negatives. Here's negative, positive. Over here is negative and positive. So in the y direction, I have a negative force due to gravity, so negative f of g. Here's my positive normal force, positive f of n. And the f of y, this is going in a positive direction, because if you look at this triangle, here's f of y pointing up. This guy is pulling at a diagonal, but that causes a vertical force in the upward direction, so it's a positive. F of y is f of a sine theta. F of a sine theta. Now this object may be moving, but that does not necessarily mean it's accelerating. So since we're doing equilibrium problems, we're going to say this is constant velocity, which means no acceleration, therefore this is equal to 0. Really, when we get to Newton's second law, we'll say that this is equal to ma. It's just that the acceleration is 0, so that's also why we have a 0 right here for right now. Okay, now I'm going to do the same thing in the x direction. Sum of the forces in the x direction. Sum of the forces in the x direction is, I have a negative frictional force, negative f of f. I have a, oh, and that's the only one other than this one. So negative f of f plus the positive f of x, which is f of a cosine of the angle theta, and there's no acceleration, 0. There you go. And that's how you do the net forces, and that's how you find the components. So when you're finding the components of an applied force, just take your applied force multiplied by the sine of the angle and applied force multiplied by the cosine of the angle to get your components. Force in the y direction and force in the x direction. Right on. How much time? Oh my goodness, 15.5 minutes. Oh boy. I have two options now. I could do the last example and make this a 21-minute long video, or just cut this video off and upload a third video. I think I'm just going to go ahead and keep going, because either way you're going to have to watch the third video, so I might as well just include it with this one. Okay. This will make this a slightly longer video, but at least it won't be as bad as that ridiculous 1 hour long video I made that one time. My goodness, that must have been torture to watch. That wasn't a joke. Okay. For this one, we're going to say we have an object that has two cables attached to it, attached to the ceiling, that are supporting a single object with a mass m. And I'm going to put in some numbers this time. This rope right here makes an angle theta 1, which is, let's see, 30 degrees. This angle right here is theta 2, and we're going to say that it's 40 degrees. And we're going to say that our mass m is 5 kilograms. There we go. Okay, and the question is, find, I'm going to call this right here, I'm going to call a tension right here, tension 1, and this is a tension 2, and I could just simply call it a force of tension in the wire. I could simply call it F of T1, or I could call it F of T2, not terminal 2, that's tension 2, but I'm just going to call it tension 1 and tension 2. You can call it whatever you want. I don't care if you want to call it avocado 1, avocado 2. Okay, and then I've also got a force going down here towards the mass. This is tension 3. Now if I draw my free body diagram for the mass, I know I've got force due to gravity going down, and I've also got tension 3 going up. That would be my free body diagram just for the mass. I'm not going to draw these. So this would be my free body diagram, tension 3 going up and the force due to gravity going down. What that means is tension 3 is equal to mg, and that's because the force due to gravity is equal to mg. So tension 3 equals F of g, therefore tension 3 is equal to mg. Okay, does that make sense? Good, 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 good. Now the goal for this whole problem is to find T1 and T2. Oh boy. So what I've got to do is take T1 and break it into horizontal and vertical components. This will seem kind of challenging, but once I work through it once, I think you'll see that it's really not too bad. I'm going to draw a triangle for T1, and I'm going to draw a triangle for T2, where I draw it in reference to the horizontal, as in I draw the horizontal line and then a vertical line and a hypotenuse going out from there. And I'm drawing them both upside down. There's my right angle there and a right angle there. I'm making T1 the hypotenuse for this triangle, and T2 is the hypotenuse for this triangle. It means that right here I have theta 1, and right here I have theta, ooh, can't really see it too well, theta 2. Okay. So I need to find, this is, gosh, I don't know how you want to call this. I mean, you guys, there's going to be a ton of variables here. I know it's a lot of variables, and you can use whatever you want to call these things. And I can't even guarantee for sure that I'm going to use the exact same variable every single time, because there are so many variables that these could be called. So let's call this T1 in the x direction. Here's T1 in the y direction. Same thing over here. T2 in the x direction, T2 in the y direction. Oops, I drew those backwards there. I'm sorry. This one is y, vertical, and that's easy to fix. Then that one is x. Okay. Just like I did before, I'm going to use SOHCAHTOA. This side is opposite, which means if you're looking at the other triangle I drew just a second ago, where did I put that triangle? Here we go. We knew that the vertical ended up being the hypotenuse multiplied by sine theta. So over here, my hypotenuse is T1, so T1 in the y direction equals T1 sine theta 1. And T1 in the x direction equals T1 cosine theta 1. That makes sense. It's just a triangle. Here on this side, I'm going to do the same thing. T2 in the x direction is equal to T2 cosine theta. Here's T2 in the y direction is equal to T2 sine of the angle theta. Oops, and I forgot to put that's theta 2, and so is that one. Okay. Now I've taken my two tensions and I've broken them down into component form. Notice in each one I've got the vertical or horizontal direction and then T1, the actual tension. Here I've got the horizontal and vertical direction and also T2. So when I'm trying to solve for T1 and T2, this will make it much easier when I've got those in my equation. Okay. Now I'm going to set up some of the forces in the x and y direction acting on mass m. So let's do the y direction first. Y direction. And I'm going to say that down is negative and up is positive, and I'm going to say to the right is positive and to the left is negative. So in the y direction, I've got a negative force due to gravity. Technically I've got the tension T3 pulling down, but T3 is equal to the force due to gravity, so I'm just going to go ahead and put right here negative mg because it's going down. Force due to gravity. Let me just go and write that a little bit more clear. Force due to gravity is mg and it's negative, so I put that right there. In the opposite direction, that's the only one that's going down, and so in the opposite direction going up, we have two positive forces, a positive T1y, and a positive T2y. And this object is not accelerating, so that is equal to 0. Now let's do the forces in the x direction. That's supposed to be a sum, not supposed to be a sum. Forces in the x direction is, I don't have any other forces than the tension, so I have T1 in the x direction, and that one is going, notice it's pulling this object to the left, so I'm going to put a negative in front of it, and a positive T2 in the x direction. And the object's not accelerating, so that is equal to 0. Now I can start solving some things. I'm going to start putting in these where I have T1, T1x, and these where I have T2x and T2y. So now I'm going to go ahead and move this mg over to this side because that's where I'm going to need it to be. So for T1 in the y direction, that's T1 sine 1, T1 sine theta 1, T1 sine theta 1, plus T2 in the y direction, that's T2 sine theta 2, equals, I add mg over to this side, mg. And I'm going to do the same thing with this one. That's a negative in front of T1 of x, so that's negative T1 cosine theta 1. Here's T2x is a positive, so positive T2 cosine theta 2, and that's equal to 0. Now you're probably wondering, while you're sitting at home watching this on a Saturday night, thinking, Mr. McGregor, you've got two unknowns. This can't be solved, can it? Well, remember, class, if you've got two unknowns, all you need is two equations. And look what we have. Two equations. Absolute rock and roll. That means this can be solved. I'm going to use the x direction because it's easier to use this one first and then plug it into y. I'm basically using substitution to eliminate one of the variables. So I'm going to bring T1 cosine theta 1 over to this right-hand side. So I get T2 cosine theta 2 is equal to, I add this over to this side, T1 cosine theta 1. I'm solving for T2 because I know what the angles are. So I'm going to solve this for T2. So I divide both sides by cosine of theta 2, and I get T2 equals T1 cosine theta 1 divided by cosine theta 2. Awesome. So this gives me an equation for T2, and look over here, I've got T2 variable. So all I have to do now is take this and put it right there. So I'm going to rewrite it, T1 sine theta 1 plus, where I have T2, I'm going to put this equation, T1 cosine theta 1 divided by cosine theta 2 multiplied by sine theta 2, and all that equals mg. Starting to look like a kind of a nightmare of a bunch of equations, but it's really not too bad. I want to solve this for T1, so I can factor T1 out of this equation, and I get T1 multiplied by the sine of theta 1 plus cosine theta 1 sine theta 2 divided by cosine theta 2 equals mg. Okay. This looks like an awful lot of sines and cosines. Fortunately, everybody in here has had geometry, so this should be pretty easy, right? It's not a joke. So at this point, I can plug in numbers if you like. I could plug in the numbers here for this angle right here and all these angles and get a number right here and mg. And if I do that, too bad I can't just simply pause this video while I plug in these thingamajigs, but oh well. Theta 1 is 30 degrees, theta 2 is 42. Actually, I love this scientific calculator. So, sine, I'm going to do the left hand side first. Sine of 30, oops, I need that in parentheses. Sine 30, parentheses, plus, parentheses, oh my goodness, I hope my calculator can handle this. Cosine 30 times sine 40, parentheses, divided by cosine 40 gives me 1.22. I'm going to put T1 times 1.22, actually it's 1.227, let's make it like that, equals mg. Well, m, we said, is 5, and g is 9.81, it just is. So 5 times 9.81, on the right hand side I have 49.05. All I have to do now is take 49.05 divided by 1.227, and I get T1 equals 39.98, whatever. Basically it rounds T1, and 2 sig figs will be 40. There it is. We've got T1, and since we have T1, now all I have to do is put it into this equation, and I'll have T2. Sounds like what we did in Algebra 2, or maybe Algebra 1 even. So I'm going to leave it as that. 40 newtons, or you can use my answer, times cosine of angle 1 is 30, cosine 30, parentheses, equals that, and then that answer divided by cosine of 40 means that T2 equals 45.2, or more specifically 45 newtons. There we go. So I went through this giant mess to get T1, and then I solved for it, and then I took T1 and put it into this nice easy equation that I have solved for T2, and just simply plugged in that 40 newtons right there, and that gave me the 45. That is a lot of work, and these are not the easiest problems to do. There is one of them on the quiz, just like this, almost, except they might give you like a T1 or a T2 possibly, but there is one of these on the quiz. Make sure you can do this. Of course, you could think about it, well, there's only one of these on the quiz. That's only 1 out of like 12, so I could just not do this and not learn this and then do okay on the quiz. Don't do that. Make sure you know how to do this, because you're going to have to learn this even more when we get to objects on a ramp. Oh, man. Yes, there's even more sines and cosines coming. Okay, you guys, that's all I have for tonight. Make sure you watch the, make sure you actually do the little worksheet that's going to go along with this. It will have some problems just like this on it for you to get practice, and it will also have a problem or two that are like this one as well, so for you to get practice with. So definitely do that. It will help you for the quiz, and I hope to see you Monday to test your bridges. Rock and roll.